Welcome to Astronomy Daily, your go-to podcast for the latest news and discoveries in space and astronomy. I'm your host, Anna. Today, we have some exciting stories lined up for you. We'll dive into new research on our moon's atmosphere, revealing the powerful effects of meteorite impacts. Next, we'll explore why detecting signs of advanced extraterrestrial civilizations, known as technosignatures, is more challenging than we might think. Finally, we'll uncover recent findings about potential dark matter objects in space discovered using pulsars. So sit back, relax, and let's embark on this cosmic journey together. NASA astronauts from the Apollo missions uncovered a fascinating aspect of the moon that was previously unknown. It has an atmosphere, although it's incredibly thin, so much so that it's technically classified as an exosphere. But what drives this tenuous lunar atmosphere? Recent research is pointing to meteorite impacts as the primary cause. When meteorites, whether large or small, collide with the moon's surface, they generate extremely high temperatures, ranging from 2,000 to 6,000 degrees Celsius. This intense heat is enough to melt and vaporize the lunar rocks, releasing atoms into the atmosphere. This process is somewhat similar to how water vaporizes when it's heated here on Earth. To get a better understanding, NASA sent the Lunar Atmosphere and Dust Environment Explorer, or LADEE, to orbit the moon back in 2013. LADEE confirmed that two main processes are at work: meteorite impacts and something known as solar wind sputtering. Solar winds, which are streams of charged particles from the sun, transfer energy to atoms on the moon's surface, causing them to be ejected into the atmosphere. However, recent studies have shown that meteorite impacts account for more than 70% of the lunar atmosphere's composition, while solar wind sputtering contributes less than 30%. The moon has been bombarded by meteorites throughout its history. Early on, these impacts led to the formation of the large craters we can see on its surface today. More recently, smaller impacts, including micrometeorites, continue to shower the moon, replenishing its atmosphere. Some of the atoms released by these impacts escape into space, but many remain suspended above the lunar surface. Interestingly, this thin lunar atmosphere mainly contains elements like argon, helium, and neon, along with traces of potassium and rubidium. Unlike Earth's atmosphere, which extends to approximately 6,200 miles above the surface, the moon's atmosphere only reaches about 62 miles high. Researchers used lunar soil, or regolith, as a proxy to study the atoms in the lunar atmosphere. By examining the ratios of different isotopes of potassium and rubidium in the soil with a mass spectrometer, they were able to trace the sources of these atoms and determine their contributions to the atmosphere. These isotopes act as historical records, preserving the imprints of the processes that have shaped the moon's atmosphere since its formation. Despite all the data collected over the years, many questions about the lunar atmosphere remain unanswered. Advances in technology, especially in the precision of mass spectrometers, are enabling scientists to gain new insights. As planetary scientist Nicole Nee from MIT explained, when Apollo samples were returned from the moon in the 1970s, the isotopic compositions of potassium and rubidium in lunar soils were measured, but no differences were observed. Today's mass spectrometers offer much greater precision. This research not only sheds light on the processes shaping the moon's atmosphere, but also helps us understand the broader dynamics at play on other celestial bodies. As we continue to study the moon, each new discovery adds another piece to the puzzle of our cosmic neighborhood. NASA scientists have been delving into the intriguing question of why we might not be able to detect advanced extraterrestrial civilizations, also known as technosignatures. One prevailing theory suggests that these civilizations may have relatively modest energy requirements, which means they wouldn't necessarily need to construct vast, detectable stellar energy structures like enormous solar panel arrays that cover their planet's surface or giant orbiting megastructures to harvest energy from their star. Let's imagine, for instance, an advanced alien civilization running on sustainable energy, much like the direction we're headed here on Earth. NASA researchers pointed out that even if humanity's population were to stabilize at 30 billion with a high standard of living, relying solely on solar energy, that would still only require a fraction, about 8.9%, of Earth's land to be covered with solar panels. It's a perspective that could explain why our telescopes haven't picked up on any massive energy structures in space. Dr. Ravi Kopparapu from NASA's Goddard Space Flight Center, who led the study, explained that their simulations show civilizations might not need galaxy-spanning energy solutions. If they achieve a sustainable balance of population and energy use, they might not feel any urgent drive to expand across the galaxy. Instead, they could be content thriving within their own stellar system, or just reaching out to a few neighboring stars. Additionally, our current technological understanding might not yet offer the complete picture of what advanced extraterrestrial tech looks like. Take, for example, huge stellar energy harvesting structures, often depicted in science fiction. These could be obsolete for an advanced civilization that has access to other space-efficient power sources like nuclear fusion. Dr. Vincent Kaufman, one of the co-authors of the study, noted that a society capable of deploying massive megastructures would likely have already developed more advanced power generation techniques that are beyond our current grasp. To put this theory to the test, the team used computer models and satellite data to simulate how an Earth-like planet with different levels of solar panel coverage might appear using an advanced telescope, such as the proposed NASA Habitable Worlds Observatory. The results showed that detecting solar panels on a distant exoplanet, even those covering a significant portion of it, would demand hundreds of hours of observing time with this kind of telescope. This highlights just how challenging it is to identify these subtle technosignatures. This research carries significant implications for the Fermi paradox, which asks why, with our galaxy's age and vastness, we haven't yet observed evidence of alien civilizations. One reason might be that these civilizations achieve a sustainable, small-scale energy balance and thus remain largely undetectable with our current methodologies. Furthermore, the researchers hypothesized that if extraterrestrial civilizations are similar to us in their reliance on silicon for solar panels, it would make detection easier since silicon is efficient and relatively abundant. However, if they utilize more advanced or alternate energy sources, the task becomes even more challenging. Ultimately, the study provides a thought-provoking reminder of the limits of our current technology and understanding when it comes to finding signs of extraterrestrial life. It's fascinating to consider that the very reason we might not be able to detect these civilizations is because they have already solved some of the sustainability challenges we are only beginning to address. This exploration into technosignatures pushes the boundaries of how we think about and search for life beyond our planet, making the quest all the more exciting. Recent research has brought exciting news in our quest to understand dark matter, something that has intrigued astronomers for decades. The study involves pulsars, which are neutron stars known for emitting regular beams of radio waves. These pulsars act like cosmic lighthouses, regularly sweeping their beams through space. By leveraging the precision of their timing, scientists have detected potential dark matter objects. Pulsars are sometimes referred to as the universe's timekeepers because of their incredibly consistent and predictable emissions. This quality makes them perfect candidates for detecting variations caused by external influences, such as unseen masses, including dark matter. So, here's where it gets fascinating. Professor John Losecco of the University of Notre Dame studied data from the Parkes Pulsar Timing Array Survey, which includes precise measurements from several radio telescopes around the world. By doing so, he found variations and delays in pulsar signal timings that suggest the presence of dark matter. What does this mean? Well, gravity has been known to slow down light for over a century, but applying this concept to pulsar timing is a novel approach. According to Professor Losecco, these variations indicate that the radio beams are traveling around something massive but invisible, likely dark matter. By measuring the delays in the arrival times of these radio pulses, which usually clock in with nanosecond accuracy, he was able to pinpoint around a dozen incidents where dark matter seems to have influenced the pulsar signals. But let's get into the specifics. When a mass as significant as the Sun interacts with these radio beams, it can cause a delay of about 10 microseconds in their arrival times. Remember, the data Professor Losecco analyzed had a resolution at the nanosecond level, which is 10,000 times smaller. One of his findings even points to a distortion equivalent to about 20% of the Sun's mass. This research doesn't just add to our understanding of dark matter, it also improves pulsar timing data, which has broader astronomical applications. Pulsar timing arrays, like the one used in this study, are also looking for evidence of low-frequency gravitational waves. Dark matter objects add what we call noise to the data. So identifying and removing their influence can make other astronomical observations more accurate and reliable. What's particularly exciting is that this refined pulsar data can be used to hunt for other phenomena in the universe. By better understanding and accounting for the influence of dark matter, astronomers can clean up the data, enhancing its precision and perhaps leading to more groundbreaking discoveries. The true nature of dark matter remains one of the most intriguing mysteries in modern astrophysics. This research by Professor Losecco adds a significant piece to the puzzle, shedding light on its distribution in our galaxy and potentially helping to decipher what it is. That wraps up today's episode of Astronomy Daily. I've been your host, Anna. If you enjoyed today's show, be sure to visit our website at astronomydaily.io. Until next time, keep looking up.